Just to recap what we have done in previous series, part 1, we have cleaned the data, then we have analyzed the data. You can see from here to your right, we looked at the different variables against each variable to see if there is any correlation. Then we've split data for our machine learning model. So let's go ahead and model our data. So just to double check, so we'll be using linear model. So the way to do is we want to predict mdiv variable against all the variables. So this is what we are trying to predict, and using all these other variables. Let's see how we predict. So it's saying there are 18 variables, 18 warnings. So just don't worry about it. It's nothing major. If you were to look at what's in the warning, so you can just type warnings. That would give us just saying do try catch, return, name parameter handler. It's not graphical parameter. Even I'm not sure what that means, but that's. Let's look at our. Let's not worry about too much about this error. But let's summarize our linear model, what we have just predict. So it gives us quite a bit details. So it gives us the residuals. You can see the minimum. If you were to plot these on box whisker plot, you'd see that's a minimum, that's first quartile, that's your median or your average, or your third quartile, and your mean and max. For each you get the estimate and the standard error, t value and p value. From here you can see that it is interesting that age does not appear to be a true factor. Similarly, text and B have minimum impact on our model, but you can see the degree of freedom, and the R square is 76, so just quite close to 1, so which is quite okay, I think, in terms of using this model. So let's further interrogate this model. Now that we have a linear model, we can now predict our test data and measure our model results against actual data. So it follows us like this. Let's check. And here's, we've got actual scatter plot. Well, scatter plot suggests it's kind of straight across, straight line, straight slope. If you were to see, it's kind of 45-degree angle. So if you were to split these in half, that would be 90 degree, and from here to here, it's about 45-degree angle. Yeah, so we appear to have close to a 45-degree regression with predicted versus actual. There is an offset. Now that we have our predictions on the test data, we need a way to measure the result. Something like sum of square as the cleanest. So in R, we don't have a built-in function, so we will have to write our own function which does sum of square. So it looks like this. So function x return x squared, and if you were to apply that for a few data, we get this. And summary, you get about sum squared about 3,500. So this is quite significant number. We'll have these in mind. Later on we'll be comparing this number with other model predictions. Here, as you can see, the sum of square result is the sum of the square of the difference between predicted and actual values. The 3000 plus values over a few hundred observations don't sound particularly accurate, but we can try out other methods to see if we can arrive at a better mode. So we will use this to compute result among the models going forward. Let's try that. Let's look at residual function. Which is, so you can see it's quite, all dots are quite close to zero. Again, when the index increases, as the index increases after 300, it goes above, the residual increases as well. But you can see it's quite close to naught. Let's try least square regression. So one might ask, what is least square regression? So the least square regression uses a line of the form b0 plus b1 times x as the line formula. So b0 as the interceptor, as I've said here, and b1 as the slope of a line, or slope of the line. So let's use the same data and see if we can fit a line on this data. And if I was to plot that, we haven't plotted the line yet. So in order to plot a line, you can see we've plotted the blue slope, blue line, the regression line. But you can see there isn't a great match between testing data and the prediction. The least square line looks too flat, so to speak. So it's not great looking at the. Some of the other machine learning technique you'd come across is the stepwise regression. So what is stepwise regression? Stepwise regression is the process of adding and removing variables from regression model, adjusting for the effect of doing so, and continuing to evaluate each of the variable involved. With the forward stepwise regression, we start with an empty model and successively add each of the variable and see their effect, decide whether they remain in the model and move on to the next variable, and so on and so forth. So you can see that's why it's called stepwise regression. So you would add and extract variable one at a time to see if that's fitting the model. So let's see how you would do that. So for that you need a package called MASS, MASS, and the way you do it is apply that, and from here you can see that starting with Indus is quite strong, Indus and age, whereas stat is quite least important in this model. This is what it's trying to say, that those are important in very has significant importance in that data set or machine learning algorithm are on top. So